Welcome to second session. Questions that people had from last week. I just wanted to pick up on a couple of points. So Conrad had asked about special bytecode or special opcodes in Monad. Were there any? He gave the example of L1 store. So I don't think there are. I think the L1 store example is significant because that's used by an L2 because there's a special messaging back and forth between the L1 and the L2. So that's why you would have those kind of special opcodes. But for Monad, no, I don't think there are. I think it is just the normal opcodes that we have there. Now, Susan had asked about the code base and the tooling. Is it all open source? Now, even though Monad do very much stress the benefits of open source, I haven't actually been able to find the code base for that yet. So I'm not sure if it's not available or what the plan is for that. If I find out more, I will let you know on that. Other questions, I think I answered last time about Monad. They have their own token. There's Mon. And then from Steve, are there other blockchains that are bytecode compatible? Yes, I mean, many chains are bytecode compatible. It does make a great deal of sense if you can do that, because it makes moving projects from Ethereum, any sort of Ethereum L1, I guess, or maybe an L2 also. But it makes it easier to migrate projects from that to a compatible chain. So yeah, Monad isn't the only one there. Okay. So that's that. Let me also, I've updated the notes a little now. I will continue to do this as we go through the course. As I have extra information, I will keep updating the notes. So please make sure that you update your browser when you come to them. Some updates I've added to lesson 1. I added in this list of the Telegram groups that you may find useful. These apply not just to countries. I think they also, for some of them, they're for languages as well. So they will be for a number of countries that share a language. But anyway, there's some groups there that you can join. I thought that would be useful for you to have a look at. So those are there. And then the other thing I wanted to do was just to mention again or remind you about the execution. If I can find that, there we go. Because we're going to be talking about gas today and gas costs, and this is quite related to execution. And so I wanted to remind you some of the features of execution on Monad that you have to remember. So of course, one of the major points is that we have this idea that we can execute transactions in parallel. And this helps a great deal with scalability. And this is done via optimistic execution. So I think that was all fairly straightforward. The other point, in fact, the one that is going to be particularly relevant to our discussion about gas, is the point about the asynchronous execution. So just to remind you, the difference here that we have compared to, say, Ethereum, is that there's a separation out, really, or the ordering of execution of transactions, and the consensus has changed. So what this involves is the fact that we can come to consensus about the transactions that are going to be in a block. But that doesn't mean that we have to have executed those transactions. So we can come to consensus about which transactions will be included before we actually know the state update that those transactions will produce. Okay, so it's a way of breaking those two, separating those two parts, and this can be quite valuable, but it does have some consequences that we need to be aware of. Okay. Of course, even though we don't know the effect of these transactions when we come to consensus about them. If you remember, I said last week, this is deterministic. So we know the order of the executions that are going to be in a block. And since the EVM is deterministic, that means that the state change is going to be deterministic. So even though we haven't actually worked it out at that point, we haven't actually executed these transactions, it is deterministic what will happen. So that's an advantage. Okay, so let me move on to lesson 2 then. And we're going to talk about gas and fees and how all these things work, and particularly the kinds of information that you're going to need to know as developers, or the information that's going to be useful to you as developers. And the first question I think is worth thinking about is why do we actually have this idea of gas on blockchains? If you think about the Web 2 world, we don't really have this concept. And we know it's tied in with the idea of the cost of a transaction and the idea of a transaction fee. And it's really tied into the fact that the main reason is that we're worried about the potential for denial of service attacks against our blockchain, against our decentralized network, because all of the nodes on our network will at some point be executing the transactions that form the block, and therefore we need to make sure that the processing that they do is not too much. It's not going to overload those nodes, and also the idea that they are going to be rewarded for the execution, the processing that they are doing, because the obviously it is, if you are running a node, it is going to cost to do that, and the execution of some code, some transactions will have a real world cost in terms of what the CPU is doing, in terms of the hard drive, etc. So that has to be accounted for somehow. We have to make sure that the people running nodes are sufficiently rewarded so that there's still an incentive for them to do that. Obviously, if it cost more to execute the transactions than they were being paid for, then there would be no point in them doing that. So for those reasons, we have this idea of the gas on a blockchain, the idea that we can get a cost for a transaction, and the gas becomes or the calculation of this becomes more complex, because we have to try to think about, when we are executing the transaction, how much computation is happening, and the more computation that is happening, effectively the more cost that is going to be passed on to the person running the node. So we have to have quite an accurate representation of that cost when we are working out the cost of the transaction. And that is why we have this idea of gas, which is meant to be an accurate representation of what it costs to execute, say, an opcode. Now, of course, there are nuances about this, and opcodes the cost of an opcode, of executing an opcode, can change depending on different circumstances. But we still have to try to make that accurate to prevent denial of service attacks. And there have been examples in the past where the cost of an opcode wasn't correctly calculated, and that did lead to denial of service attacks against blockchains. So that's why we need to go through this whole process, and we have to try to make sure that the gas cost is an accurate representation of the real world cost. So this, of course, for Ethereum, they've been developing this for a long time, and they've been able to adjust the gas cost for opcodes over time, and they've got sort of fairly good at that. It's become fairly accurate. They have also gone through a change in the way that works as well. They've broken down the cost of a transaction into a base fee and a priority fee. And then this also is the way that Monad have continued with that. So yeah, that's what I've got here in the notes. So we need this idea of gas because it's going to work out the cost of a transaction, and it is going to depend upon the complexity. We have this idea of a base fee. Now, the reason that it's useful to split out this base fee and the priority fee is that we want some mechanism within our network to act as a something dynamic, to help us get an equilibrium, to prevent our network being overloaded by transactions. So this different networks do this, different blockchains do this differently, but the idea that the Ethereum has followed is the concept that there is a kind of a back pressure applied as we get more transactions coming into the network and more demand for those resources. Then we have to apply a kind of a back pressure to try to discourage more people from putting transactions into the network. And this is done by increasing the base fee. And so if the base fee increases, this should hopefully reduce demand, reduce the amount of transactions that are coming into the network at that particular time, and therefore reduce congestion. So this, by the use of this base fee and the fact that this can be determined by the network, by the validators in the network, then we can get a nice equilibrium, a nice dynamic equilibrium to try to prevent the network being overloaded. Yeah, I've got the point here. I think I've actually may have. Yeah, so the base fee at the moment on the test network is hard coded, but this is going to change in future. So just do be aware of that. That it's not always going to be hard coded. And then on top of that, the other part of the fee that you're going to be paying for your transactions is the idea of a priority fee. And we want this because users may want to ensure that their transactions are included quickly. And so there's the users are providing demand for block space. And then the network is, and the validators, the block producers are providing that block space. But if there is congestion, then maybe people would want to increase their priority fee to make their transactions more attractive to the block producers, so that they are more likely to be included in a block. And also the idea maybe that they want to get their transaction included ahead of other transactions also. And this leads on to all kinds of interesting behavior that I'll touch on in a second. But the basic idea then is that our transaction fee is going to be a mixture of these. But also there is something special with Monad actually that you don't get on other blockchains, and that there is an extra cost that is charged. And this is to do with the inclusion of the transaction at consensus time. And this is a consequence of this fact that we've got asynchronous execution, and therefore we have this idea of the transactions being included, and we come to consensus about those transactions. And as part of that, we have an extra cost included in the total cost, which is charged for that transaction being included at consensus time, and that kind of applies at that time before it is executed. Now the name of this has changed, and I'm not sure what the correct terminology is at the moment for this. It used to be called carriage cost, but it is changing. So I've just called this extra cost at this point. Now, another point about the way that Monad works and how this affects the cost of the transaction fees. due to the way that execution works, is that, again, because we have this asynchronous execution, when we have the consensus happening, we've decided upon the transactions within a block. We don't know at that point how much computation is going to be needed for all of those transactions. Those transactions haven't been executed yet, so we don't know what the cost of that is going to be. And so to sort of be on the safe side, what the validators can do at that point is to charge the entire gas limit, because they don't know how to do anything more accurate at that point. So each block will have a gas limit. This is the total amount of gas that the total amount of computation that can be done within that block, and often this is seen as really the sort of the amount of computation that can be done, the sort of computation throughput of the chain. So yeah, so we have this special case in Monad that because the validators can't accurately say what that is when they are including when we're getting to consensus, then they're going to charge the gas limit at that point. Yeah. Now, this could all change. So this is the way that things work at the moment, but it may change, and it's important as you're developing. It's important to bear in mind that this could lead to the way that your contracts behave. That may change in the future. So just be aware of that this could change the behavior of your contracts. So yeah, I just wanted to stress that. Okay. This idea of the PGA, really, this is just the priority fee that I've mentioned before. The idea that if you are prepared to put in a higher price, then your transactions will get ahead of the rest of the transactions for that block. Now, all of that kind of idea goes into the concept of called MEV, which is a general concept. It's really an emergent behavior that people have found that has happened with the more complex blockchains where we do have computation happening. So, for example, Ethereum is less obvious on simpler blockchains like Bitcoin, but it's all about the fact that there is a demand for block space. There are certain actors within the system, so the block producers or the leaders who are going to choose the transactions, and therefore there is value that can be extracted by the block producers for including transactions in the block or including transactions ahead of other people. But that's a huge topic which I'm not going to go into at the moment. Now, another point that you'll come across when you're looking at the way that the transaction fees work, which is tied into this idea of the asynchronous execution, is that we have two balances for each account. And the first one here, this balance at consensus. This is what is used to pay for this additional cost that I mentioned. So this extra cost that is in part of you could look at it as the overall cost of the transaction, but it is part of that is separate from the base fee and the priority fee. This additional cost is taken from the balance at consensus. Okay, and this is done via from the validators, and then the normal cost is taken from the execution balance. So the normal cost of the transaction is taken from a different balance. Okay. And this is all to do with the idea that we want to be careful to make sure that when transactions are included within a block at consensus time, then they don't go on to fail when they're actually being executed because they're running out of gas. So it's to try to get that balance and get that confidence about our transactions. So these are all consequences of the fact that we have this notion of asynchronous execution, and the fact that when we agree to the transactions that will be included, we don't actually know fully what the cost of those transactions is going to be in terms of computation. Now, this is then this then goes on to this this point about the this delay period as well. This really is what I'm saying here, with the idea that we have this this is relating to the balanced consensus there, and so it's making sure that we can pay for any transaction that would otherwise fail. Okay. All right. Now, that's really concentrating on the idea of the asynchronous execution. Other points about Monad's architecture and how this affects the fees. Well, generally, Monad is really concentrating on scalability and being very efficient at the way the components work together. And all of this is designed then to try to reduce the fees that would get charged. And this partly comes from the fact that we can, if we have faster block times and have greater throughput, this means that we've got more transactions going through. So the cost from the network of sort of maintaining the network then will get borne by more transactions. So it decreases the cost per transaction overall. So it should. The idea is that then this will give lower fees in general. Okay. Other points about the way that the consensus mechanism works. Once a leader has created a block and decided what that block's going to be, this needs to be propagated then around the network. And I said that the original ways of doing this are quite sort of original blockchains using gossip protocols. That is quite inefficient. It's better to be more focused in how transactions move around and how blocks move around. So we saw that with transactions, we can send those to the leader or the leader plus one, etc. But then also you have to think about the blocks being distributed, and so they have this protocol called Raptorcast, which also improves the performance of that. Now, this works by just making it the way that the blocks are distributed, making them more efficient. It's done through this idea of building out a tree with recipients and sending those there, which reduces the overall network costs of passing the blocks around. But if you want to know more about that, then there's links to details about that. The idea is that it is trying to just make this propagation much more efficient and not waste bandwidth when it is doing that. Okay. So I think I've actually covered much of this already. Some of the points here, the idea of the asynchronous execution, which reduce we get better throughput, so we can reduce the overall gas consumption. Similarly with parallel execution, I think I've sort of gone through all of these already. And again, really all of these optimizations, the fact what they do in effect is to reduce the cost, the overall cost. They make the blockchain more efficient, and therefore they're reducing the cost for your transactions that they need to pay to keep the network going. So that's what these details are all about. Okay. In terms of the format, they they're equivalent. They maintain compatibility with Ethereum, which is going to help. It means you can use the tools and the such as block explorers, such as wallets that you have used on Ethereum. And this point here, I really mentioned it already, that we, even though we don't execute the transactions straight away, we defer that, or it's asynchronous, we still get determinism because the EVM is deterministic. Okay. All right. Let me move on. And I want to talk a little bit about optimization. And really, this is just an introduction, but it's to help you when you are writing your code, to help you optimize that. But I should start off with some caveats about this. And I've had a lot of experience of seeing people optimizing code, even before Web3, and people, developers, and I'm also tempted to do this. They do like to tinker with code and try to make it optimal and reduce the cost, but we often do this at very much the wrong time. And what you should be doing is optimizing your code once it is very much finalized, once you are not going to make any substantial changes to that code. And certainly the most important aspect of your code is that it is secure, that it is accurate. There are no security problems about it. So that should always be your first priority. Get your code correct, make sure it is working as intended. And then at that point, then start to look at the optimizations that you can do. Now, when you're doing that, you also have to be clear about what you are optimizing for and what performance will be acceptable to you. If you want to, you can spend a long time sort of optimizing and getting smaller and smaller gains in terms of the gas that you're going to be spending, reducing that. But at some point you should stop and say that you've reached an acceptable level for that. So be aware of that. Also be aware of the scenario that you are optimizing for. So when you're writing your code, there's going to be a cost for deploying that, and that could be what you're optimizing for. So, for example, reducing the amount of bytecode is going to make for a cheaper deployment. So maybe that's going to be your target, or perhaps you're going to be thinking about what is happening at runtime and the functions that are being called, and trying to reduce the cost of those. Of course, that cost is going to be borne by your users. So whether that, how important that is to you, is going to be all about your business and the use case that you have. But when you're thinking about optimization, you need to make these decisions up front before you start the optimization process. You should always have some unit tests to make sure that when you change your code to optimize it, that your code is still working correctly. So I'm assuming that, because that really is something that you should have. So I'm making that assumption that you will have done that already. And then the actual steps that you will want to go through for optimization. The first one is to measure the performance. And as I said, the context can be important here. But you need to measure the performance. And I would say that in blockchains and in Solidity, this is particularly important, because it can be quite counterintuitive, the effect of an optimization that you introduce. So you may think that you may change a function in a certain way and think that is going to reduce the cost at runtime, for example. But if you measure it, you may find that actually it increased the cost, and it is often quite counterintuitive. So always measure the performance. It's also the case that you should be measuring the performance so that you have a good idea of what is the most expensive operations within your contract, and where to put your focus, where to put your effort when you are optimizing, because you're going to want to focus on the things that will give you the best return, the low-hanging fruit for optimization. So measure the performance, then decide on the change that's going to have the most impact. Make that change. Make sure that the code is still correct by running your unit tests, and then go back and measure the performance again and make sure that the change you made did in fact improve the performance. And then if that's the case, great. You can go on to decide on the next change, and then just go around this loop again and again. All right. So let me go on to some techniques that may help you reduce the amount of gas in your contract. Some of the easiest ones, and some that will give you the best results, are actually just to remove functionality that is no longer needed. Again, I think it's very tempting for developers. We like to make our code very generic, and we often put in functionality that isn't really needed in our code. And so by the time you've come to the end of the development process and your code is pretty much finalized, you should know then whether there's some functionality that's not actually going to be needed, in which case you could potentially remove that code, and that could reduce the cost, particularly at deployment time. So be very focused on that. That may well be the easiest optimization that you can do. Other ones, and really these are in no particular order, but things like taking shortcuts. If you have a loop, break out of that loop as soon as you can. So imagine you've got a loop, you're looking for a particular value, you find that value, well, break out of the loop. Don't continue going around that loop. That's extra expensive computation that is not needed. Also, if you have functions that are where one is expensive or one is cheaper, then if you're going to get results from the functions, and you're using that, then you're using some Boolean logic on that, then this you should be doing the low cost function first. So here we're saying we want A or B, so we would do A first. That's the cheaper one. If that comes back as true, then we don't need to run B. And then similarly, if we're doing an AND, we can run A first as cheaper. If that comes back as false, then we don't need to run B, because the whole thing will be false. So that kind of ordering will help also. Obviously, this is really about runtime. Storage. This is one of the most expensive operations that you're going to be doing in your code. So it makes sense to reduce the amount of storage as much as possible. So first of all, so only store what is absolutely necessary in variables, and that's going to give you big savings in terms of gas. Also, the way that the gas is calculated for storage is dependent upon various things. It's become a little bit complicated, so I've got some of the details there. So you can think about this as well, but really the big saving you'll get is by just not storing things unless you really need to. So, for example, you could try storing things elsewhere. So don't put things into variables, into storage, if they can be put elsewhere, and we'll talk about that in a second. And then also, for example, if you have some calculation which has some intermediate steps, don't write those steps back into storage if you don't need to. Just put the final results back into storage. So some of the alternatives you have are using memory, which is going to be cheaper than storage, but it still has a cost, and there is a cost of moving between memory and storage. So again, you should be measuring these things. You measure the cost to make sure it's still worthwhile. Do be careful as well to make sure if you're doing this and moving between memory and storage that you keep them in sync, and don't forget to write values back to storage when they're needed, because projects have been wrecked by that. The cost of memory is complicated in how it is calculated. Initially, it's cheap, and then when you get past 724 bytes, it becomes increasingly expensive the more memory that you want to use. Other points: avoid excessive checks. If you find that you because of the logic of your contract, you may be able to determine that a particular check done earlier on in the contract still applies. So therefore, don't do that again. You'll save gas by doing that. Other points: packing. This applies when you have storage. You can put multiple variables within one storage slot. If you can do that, that will reduce the number of store operations that will be done. So this can save you gas, but as you can see here, we've got 4 fields in a struct, and we're going to store those. What the optimizer has been able to work out is that actually we only need 2 storage slots for these 4 items, and therefore we only need to do 2 store operations, as long as we can put them as you can see here. So the first 3 go into one slot, and then the final one goes into the final slot. So the optimizer has been able to do that, but it's not going to rearrange the order of your items. So you have to have the items in the right order so that it can do this type of optimization. Now, you might think then, well, great, then generally smaller data types are going to be cheaper than larger data types. Well, it's a little bit more nuanced than that, because even though when we're storing these items, we could end up with fewer store operations, when we are then using these items, we want to take these items out of storage and they'll go onto the stack. This requires extra computation, because you have to do some masking and just take part of the storage slot. So there is additional cost alongside that if you are putting multiple items into a slot. So again, measure all of this to make sure that if you do change the size of some variable, that does give you a benefit. Okay. All right. I'm not. So let me just check. Sorry, I'm not seeing any questions. So I'm hoping that means that you don't have any questions. But please, if you do have questions, please pop them on Slido. Okay, so and also let's have a quick look at the poll while we're here. So we've got quite an interesting range. We have NFTs and meme coins sort of equal, about 24% there. A little bit more on other DeFi, so other DeFi projects on 31%, and then a little bit less on SocialFi, 14%, sorry, and then GameFi on 8%. Okay, so we're very much in the DeFi realm, which is either NFTs, meme coins, or other DeFi even more popular. So thank you for that. That's very interesting. I'm going to actually switch over quickly from that. We can come back to that later, but I'll just switch over now to this poll, which is about your preferred tool chain when you're developing Solidity. So yeah, let me know. Okay, so other items here. So other optimizations we can do. Well, when we're doing loops, obviously the item that's in the inner part of the loop is going to be that's going to be executed most often. So if you did something like this first example here, where this num variable is actually a storage variable, as you can see. Each time we add one to it, then that means we are reading it, and then we're writing it back into storage. So this is going to be a very expensive loop. A better way to do this is to do the loop you can see here, where we put this into a local variable, this temp variable here. That variable, because it's a local variable in the function, will exist on the stack, and which is cheap. Then we can do our loop and write to that, and then only write back to storage at the very end. So we only have one storage, one store opcode being done right at the end of the after the loop is finished. Of course, with something like this, you could predict the values anyway. I mean, this is such a simple example that you don't really need to have a loop to do this. So if you can predict values ahead of time, then yeah, that's even better. So yeah, but be aware of that when you have loops, that the inner part of the loop is going to be executed a lot. So make sure that's very cheap. Also, reduce the number of items you go around the loop if you can. It's always good to have an upper bound to loops. That is also for security as well. And break out of the loop as soon as you can also. Other miscellaneous optimizations, make sure you use the optimizer. You usually have the option of this when you're compiling your code, and you can make adjustments to how many times the optimizer is going to run. So be aware of how the optimizer works. Make sure that you are using it, and set the number of times it runs. And the number of times, the rule generally is that if you have a lower number, that will optimize more for deployment time, and a higher number will be better for runtime. What I would suggest, though, is that you experiment with this and try out a few different numbers. Start at 1, go up. Oh, yeah, because the default is 200, but start at 1, try a few numbers up into a few thousands, and see if you can find a sweet spot for your code that for the optimization, for the optimizer. Sorry. Other points as well. Use libraries. If there's an existing library on the blockchain that does some functionality that you want, well, you can use that. It will save you having that bytecode within your contract, and therefore you having to pay for the deployment cost of that. Of course, there is a cost to making the call to the other to the library, but yeah, again, this is going to depend upon whether you're optimizing for deployment or for runtime, and again, yeah, measure that and make a decision once you have an accurate figure. For measuring this, I mean, I keep saying measure it. So how can we measure this? Well, there's a number of ways. There are Web3 functions that you can use to do that. Also, in the tool chains, there are plugins that will help you. That's probably the best way to do it. Yeah, something like the Foundry plugin, the Gas Reporter plugin is very good. It will tell you, deployment cost. It will tell you the cost of various functions. So yeah, they're great to help you with that. Another useful tool is the Sol2UML tool, because this is good not for the UML aspect actually, but it gives you a visualization of the storage slots within your contract. So that can be very useful to help you understand if you're trying to pack data. It gives you a visualization of how you've been doing with that. Okay, let me move on. So comparing with other chains, I think this has come out slightly wrong actually. I'm sorry about that. I should have had other chains to compare with. So this is well, this really is just comparing to Ethereum layer 1, but it's to give you an idea of, particularly around things like the costs of transactions and scalability as well. So there's just the main points here around that. I don't know if there's anything that needs to be really highlighted. Obviously, we've got the throughput that is being aimed for here is obviously vastly different. The block time, it's half a second on Monad. The gas fees, again, you're aiming for much lower gas fees as well. Consensus mechanism, I've spoken about that, but that's just a reminder there for you. And it's fully compatible in terms of the bytecode, which is great. So you can just you can easily migrate projects from Ethereum to Monad. So we've got bytecode compatibility. The one point about this transaction throughput is really then it sort of guides us as to the types of applications that would make sense. So if you're thinking about applications, and particularly I'm thinking here of DeFi applications, where we're moving towards some of the concepts of things like high frequency trading, where we need a lot of transactions going through a network, then obviously this is an area that Monad is going to be able to handle much better than Ethereum, which is not going to be, you're not going to be able to get that many transactions through the network. So those types of applications are going to be a good use case, a good reason for choosing Monad over Ethereum. What should have been in the table as well was a comparison with other chains like Solana. So I'll just mention that quickly as well, because Solana is, came out to 2018-ish, that kind of time, sort of initially, and it also focused very much on performance and throughput, and has managed to achieve that using some of the same ideas around parallel execution, etc. Although their version of their way they've done that is perhaps a little bit less sophisticated than what is being done with Monad. So so that's also another chain that is focusing on scalability and throughput, but then they're not EVM compatible. So it's not as easy to move a project from Ethereum to Solana, even though you do have you can use the Solidity language on Solana now, but it's not really the same. It's because the way that programs work are quite fundamentally different. So so that's another difference then between Monad and say Solana, and then other sort of more recent chains that are similar to Solana, like Aptos and Sui, etc. We've spoken about this. I perhaps don't need to say much more about that. The mempool we talked about briefly last time. Again, this is all about efficiency when we're moving our transactions, so getting them to the right place and not doing sort of excessive network traffic. So it's being very much more focused. Other points about this, when I mentioned MEV earlier, this is very much about, also it sort of comes into the idea of the mempool as well. So this may be something you would be thinking about, because if transactions are within a mempool for a long time, this can mean that they are more prone to, say, front running those those kind of behaviors. It's not something I've got time to go into at the moment, but you can have a look at that. This is something you do see on Ethereum, where we have transactions, in a public mempool for much longer because of the block time. If you have a faster block time, then there's less time for that to people to react to what's in the mempool. So it's less of an impact. Okay. Security features. The BFT consensus is seen as being a very secure mechanism as well. It is, the fault tolerance is built into that. There are plans also to employ measures to incentivize correct behavior from the participants in the network as well. It's a similar way to Ethereum as well. Developer tooling, really, I've mentioned this, that we can use the same tools that we have on Ethereum as well. So that's a great advantage. And thank you for the votes in the poll there. I see that Foundry is just in the lead, 48% to Hard Hat, which is on 42%. So yeah, that's interesting. Next week we'll be looking more at the practical aspects, and I have got more details about using Foundry with Monad as well. So I think we'll concentrate on that anyway. One point here that's useful to know: the contract size. This can be a problem when you start to do real projects. You may find that the contract size is not enough on Ethereum. There are ways around it, but it still can be problematic. So it's useful that we have this. We have a greater maximum size of our contracts, so we don't have to hit that. All right. I'll just quickly talk about the testnet. I've got a link there to a video from ETH Denver talking about some of the aspects of Monad. So it's quite a nice video. It talks all about the architecture and the components, etc., that we've been discussing. So do have a look at that. And then obviously the testnet started to the beginning of February time, and yeah, it's got up to when this presentation happened, it was about 250 transactions per second that were going through, and had about 60 validators. So you can have a look at that. You'll see details about that. If you're going to be using the testnet, there is a faucet. Unfortunately, this seems to be having problems at the moment, but there's a link there to that. So do try and get some testnet mon. I think it is struggling, so it will fail quite often. But anyway, there's details. It also has details of how to add the network to whatever wallet you want to use. This is quite nice. There's a visualization here of the validators, as you can see, producing the or the leaders producing the blocks, and the blocks going up there. Oh, there you go. The TPS at the moment, 339. Of course, this doesn't mean that that's the maximum. It just means that that's how many transactions we've got going through at the moment. It doesn't mean it's being stressed particularly. That's quite a nice site to have a look at those things. All right.